Welcome everyone. I'm excited to have you here today. Today's presentation is about the Analytical Applications Department at Shimadzu Corporation. The focus will be on HPLC basics, which are fundamental to our work. Over the next few slides, we'll explore key concepts and applications of HPLC technology. Let's get started. Let's start by understanding what chromatography is. Essentially, it's a powerful technique used to separate components within a mixture. This separation allows us to analyze and identify individual substances more effectively. Moving on to the outline of HPLC analysis, or high-performance liquid chromatography, we can see it involves several key aspects. First, the separation mechanism. This is how the different compounds are distinguished from each other as they pass through the system. Next, we have the hardware mechanism, which includes all the equipment and components that make this process possible. It's fascinating how these sophisticated instruments work together to achieve precise separation and detection. Throughout this presentation, we'll explore both these mechanisms in detail, connecting how they contribute to the overall effectiveness of chromatography, especially in complex analytical tasks. So, let's delve deeper into each of these points to see how they fit into the bigger picture of analytical chemistry. Chromatography is one of the key separation techniques we use in analytical chemistry. Its main goal is to separate and quantify our target sample within a complex matrix, which could be anything from blood to environmental samples. By doing this, we can identify and measure specific components accurately. Now, today we're focusing on HPLC, or high-performance liquid chromatography, which is a highly efficient form of chromatography. It allows us to achieve rapid and precise separations, making it invaluable in many industries. So, to sum up, chromatography in general is all about separating mixtures, and the main purpose is to analyze and quantify the components of interest. It's a cornerstone technique that underpins many of the analytical methods we rely on in research and quality control. Today, I want to talk about some key concepts related to chromatography. First, let's look at colors. Colors play a crucial role in chromatography because they help us identify different compounds once they are separated. Next, chromatography itself is a fascinating technique used to separate mixtures, often based on how different substances move through a medium. Chlorophyll is a great example of a compound that can be separated and studied using chromatography, especially in plant studies. Then we have Ca-CO3, which is calcium carbonate, a common substance that can also be analyzed through this method. Ether, on the other hand, is an organic solvent frequently used as a mobile phase in chromatography because of its ability to dissolve various compounds. Now, a brief historical note. Chromatography was invented by M.T. Sweat. His discovery was pivotal because it opened up new ways to analyze complex mixtures. Understanding this invention helps us appreciate how chromatography has become such a fundamental tool in chemistry and biochemistry today. All these points connect to our overall theme of how we identify and analyze substances efficiently, which is essential in scientific research and practical applications. On this slide, we're looking at the core components of a typical isocratic elution system in chromatography. First, we have the single solvent, which is the liquid mobile phase that carries our sample through the system. It's important to choose the right solvent because it directly affects the separation quality. Next, the detector plays a crucial role. It identifies and quantifies the analytes as they pass through, giving us the data we need. The oven helps control the temperature, ensuring consistent conditions for reproducibility and optimal separation. The column is where the actual separation happens. It's packed with the stationary phase that interacts with our compounds. The injector introduces the sample into the system smoothly and precisely. The pump then pushes the solvent and sample mixture through the column at a consistent flow rate. And finally, the isocratic elution system uses a single solvent throughout the process, which simplifies things and helps maintain stable conditions. All these components work together seamlessly to deliver reliable and efficient analysis, which is the overall goal of chromatography. So why can a mixed sample be separated? Well, it all comes down to the asterisk direction of flow and the asterisk river bed asterisk. When a mixture of particles or substances is carried along a flowing medium, like water in a river, different components tend to move differently depending on their properties. The asterisk direction of flow asterisk influences how these particles travel. Some may settle faster, others might be carried further. Imagine a river bed with various features, like bends, rocks, and sediments, that affect the flow paths. These features create conditions where different particles are separated naturally. This is why understanding the asterisk river bed asterisk and flow direction is key to grasping how separation happens. In essence, by controlling or understanding the flow direction and the characteristics of the river bed, we can effectively separate mixed samples based on their physical or chemical properties. This concept is fundamental in many separation techniques used in environmental science, engineering, and even in industrial processes. So let's focus on week 7, where we really dive into understanding what makes a strong interaction. Now, at its core, the idea is that gravity is what keeps things together and influences how objects interact in our universe. But the big question we're asking here is, what exactly is the difference between different types of interactions? Throughout this week, we'll explore how gravity compares to other fundamental forces and why it's considered unique. We'll look at how gravity operates over long distances and how it governs the motion of planets, stars, and even galaxies. By the end of this week, I want you to see that understanding these differences helps us grasp the bigger picture of how the universe functions. It's about seeing gravity as a key player that shapes the cosmos, but also recognizing how it differs from other forces we encounter in our daily lives. This is a crucial piece of the overall theme, understanding the nature of forces and interactions that define the universe's structure. So, let's get started and really unpack what makes gravity such a strong and fundamental interaction. All right, let's talk about the packing material first. When we're dealing with separation, a common choice is a packing material with particle sizes around 3 to 5 micrometers. This size range is quite effective because it provides a good balance between surface area and flow resistance, which is essential for efficient separation. Now, moving on to the separation process itself. It can actually be performed right within the column. The column acts as the main arena where the separation happens, thanks to the packing material we just discussed. As the mixture passes through the column, different components interact with the packing material in unique ways, allowing us to separate them effectively. So the key point here is that the column is not just a container, it's the critical component where the separation occurs. This flexibility to perform separation within the column itself is what makes this technique so powerful and widely used in various analytical and preparative applications. And as we continue, remember that choosing the right packing material and understanding where and how the separation happens in the column are fundamental to achieving good separation efficiency in your experiments. Now let's look at sample B and sample A when it comes to packing material. The key point here is that, because of the different ways the packing material interacts with each sample, we can actually perform separation. This interaction, which we're calling interaction 1, plays a crucial role. Essentially, the way each sample reacts with the packing material allows us to distinguish between them. This is an important concept because it highlights how the choice of packing material can be used strategically to facilitate separation processes. So, understanding these interactions helps us optimize our methods and improve the accuracy and efficiency of our sample analysis. Now, on this slide, I want to highlight how the separation process really depends on the different interactions among the packing material, the mobile phase, and the sample itself. Essentially, these interactions are what allow us to separate components effectively. Think of the packing material as the stationary phase, which interacts with the sample components in various ways. The mobile phase, on the other hand, acts as the moving solvent that carries the sample through the system. The key point here is that the differences in how each sample interacts with both the packing material and the mobile phase are what enable us to achieve separation. When these interactions vary among the components, it creates different rates of movement through the system, allowing us to distinguish and isolate each one. So the overall idea is that the separation isn't just about pushing everything through, it's about the nuanced interplay between these three elements: the packing material, the mobile phase, and the sample itself. That's what makes chromatography such a powerful technique. Let's take a closer look at this slide, which focuses on the concept of separation in the column during chromatography. As you can see, we have a column, and within it, different components are separated based on their interactions with the stationary phase. This separation is crucial because it allows us to distinguish and quantify individual compounds in a mixture. Now, moving to the chromatogram, this is the visual output we get from the separation process. The peaks on the chromatogram represent different substances as they exit the column at different times. The key points to note here are the time and concentration axes. The time, often called retention time, tells us when a particular compound elutes from the column, while the concentration indicates how much of that compound is present at a given time. Understanding the relationship between these two helps us identify and quantify compounds accurately. The separation process, the shape and position of the peaks, all provide valuable information about the mixture's composition. So, in essence, this slide highlights how the separation process in the column directly impacts the chromatogram, which is fundamental for analyzing complex mixtures in our overall analytical methods. All right, let's take a closer look at this chromatogram. Here, we're focusing on some key terms that help us interpret the data. First, we have H, which stands for peak height. This is the maximum response of the detector for a particular compound, giving us an idea of its concentration. Then, there's A, the peak area, which is actually a more accurate measure of the total amount of compound present because it accounts for the entire peak, not just the maximum point. Next, T0 represents the non-retained time, which is essentially the time it takes for an unretained compound to pass through the system. This helps us establish a baseline and understand the system's inherent delay. Moving on is the retention time, the time it takes for a specific compound to travel through the chromatography column and reach the detector. This is crucial because it helps us identify compounds based on their unique retention times. Finally, the diagram shows the response of the detector over time, plotting the peaks at different points. The peak response corresponds to the compounds eluting from the column, with the position and size of the peaks giving us valuable information about their identity and quantity. Understanding these concepts is fundamental in analyzing chromatograms accurately and connecting the data to the overall separation process. All right, let's take a closer look at this calibration curve. As you can see, it's a key part of our analytical method. Here, we're plotting the peak areas against the known concentrations of our standards, which are labeled from C1 to C4. These C values represent the concentrations of our external standards, and the corresponding values, A1 through A4, are the measured peak areas for each standard. The main idea here is that by establishing this relationship, we can accurately determine the concentration of unknown samples based on their peak areas. Notice how each peak area correlates with its respective concentration. This is the essence of calibration. Now, when we plot these points, ideally, we get a straight line, which indicates a linear relationship. This linearity allows us to interpolate or extrapolate the concentration of unknowns from their measured peak area. This process is fundamental because it ensures our measurements are reliable and repeatable. External standard calibration, as shown here, is a common approach in analytical chemistry, helping us quantify substances with confidence. So, in the broader context of our presentation, this calibration curve ensures the accuracy of our quantitative analysis, which is critical for the validity of our results. Let's take a closer look at how we calculate our results. On this slide, you see the number 2500, which represents the peak area we obtained from our analysis. When we talk about concentration, such as the 125 mg/L shown here, we're referring to the amount of substance in our sample. The key concept is that there's a direct relationship between the peak area and concentration, which we express using the equation y equals a x plus b here. Y is the peak area, x is the concentration, o is the slope, and b is the y-intercept. In our case, the slope indicates how much the peak area changes with each unit change in concentration. The y-intercept b is the value of the peak area when the concentration is 0, basically, where our line crosses the y-axis. By knowing these parameters, we can accurately calculate unknown concentrations from their peak areas using this linear equation. This is fundamental in analytical chemistry because it allows us to convert raw data into meaningful concentration values. So, understanding the slope and intercept helps us interpret our results precisely and ensures the reliability of our analysis throughout the process. So let's dive into what chromatography actually is. Essentially, chromatography is a powerful technique used to separate different components within a mixture. It works by exploiting differences in how substances move through a medium, allowing us to analyze complex samples effectively. Now, focusing on HPLC, or high-performance liquid chromatography, we can think of it as a refined version that offers high resolution and speed. When we talk about the outline of HPLC analysis, there are a few key aspects to consider. First, the separation mechanism. This is the core idea of how components are separated based on their interactions with the stationary and mobile phases. Different compounds will travel at different rates, allowing us to distinguish them. Next, hardware mechanism refers to the actual equipment involved, like the pumps, columns, detectors, that make this separation possible. Each component plays a crucial role in ensuring accuracy and efficiency. Lastly, the contents of this slide give us a roadmap of these topics, helping us understand the fundamental principles behind HPLC analysis. By grasping these points, we can appreciate how chromatography, especially HPLC, is such a vital tool in analytical chemistry, enabling us to identify and quantify substances with great precision. Understanding the separation mechanism is really crucial if we want to obtain reliable and consistent results from our chromatography experiments. Today, I'll mainly focus on reversed phase chromatography, which is one of the most commonly used methods. The key idea here is that the separation depends on how well the analytes interact with the stationary phase versus the mobile phase. In reversed phase, our stationary phase is nonpolar, usually made of C18 chains, while the mobile phase is more polar, like water mixed with organic solvents such as acetonitrile or methanol. This setup means that compounds which are more hydrophobic tend to stick longer to the stationary phase, while more polar compounds elute faster. So, the separation mechanism is largely based on differences in hydrophobicity among the analytes. Recognizing this helps us optimize conditions, like adjusting the organic solvent percentage, to improve separation. Overall, understanding this mechanism is essential because it guides us in method development and ensures our results are both accurate and reproducible. Now, let's take a closer look at the various separation modes of HPLC. First, we have the normal phase mode, which uses a polar stationary phase and a nonpolar mobile phase. This mode is particularly useful when separating compounds based on polarity differences. Next, there's the reversed phase mode, the most commonly used in HPLC today, where we have a nonpolar stationary phase and a polar mobile phase. This setup is ideal for a wide range of analytes, especially in biological samples. Moving on, we have the reversed phase ion pairing mode, which is a variation that allows us to analyze ionic compounds more effectively by pairing them with an oppositely charged ion. This enhances retention and separation of charged molecules. Then, there's the ion exchange mode, where separation is based on the charge properties of molecules, making it excellent for separating ions and polar molecules. Finally, we have SEC mode, or size exclusion chromatography, also known as GPC or GFC. This mode separates molecules based on their size, which is especially useful for analyzing polymers or biomolecules like proteins and enzymes. Understanding these different modes allows us to choose the right approach depending on the properties of the analytes we're working with, ultimately improving our separation efficiency and analytical results. All right, let's take a closer look at the table comparing normal phase and reversed phase chromatography. On the left, we have the stationary phase, which can either be normal phase or reversed phase. In normal phase chromatography, the stationary phase is hydrophilic, meaning it has high polarity. This makes it attract polar molecules. Conversely, in reversed phase chromatography, the stationary phase is hydrophobic, with low polarity, which tends to attract nonpolar or hydrophobic molecules. Now, looking at the mobile phase, the roles are reversed. In normal phase, the mobile phase has low polarity, so it's less attracted to polar substances, allowing polar analytes to interact more with the stationary phase. In reversed phase, the mobile phase is high in polarity, which helps elute nonpolar compounds from the hydrophobic stationary phase. What's important to note here is that these two modes are essentially mirror images in terms of their polarity interactions. Understanding this helps us choose the right method depending on whether our target analyte is polar or nonpolar. This fundamental difference in phase polarity directly influences how compounds are separated during chromatography, which is key to optimizing our analytical methods across various applications. Now let's look at the degasser status. When the degasser is off, the system isn't actively removing gases from the solvents, which can sometimes lead to bubble formation or pressure issues. Turning the degasser on helps eliminate dissolved gases, ensuring more stable and reliable chromatography results. Next, consider the solvents involved. N-hexanes, ethanol, and IPA. These are typical solvents used in different modes of chromatography. N-hexanes is a nonpolar solvent, which means it interacts differently with analytes compared to polar solvents like ethanol and IPA. Speaking of properties, it's important to understand nonpolar versus polar properties. Nonpolar solvents tend to dissolve nonpolar compounds, while polar solvents are better for polar compounds. This distinction influences how we choose our mobile and stationary phases. In chromatography, the mobile phase is the solvent moving through the system, carrying the analytes, while the stationary phase stays fixed inside the column. The key here is the polarity of these phases, which determines the mode of separation. In normal phase mode, the stationary phase is nonpolar, and the mobile phase is polar. Conversely, in reverse phase mode, the stationary phase is polar, and the mobile phase is nonpolar. Specifically, if we look at the stationary phase as nonpolar, and the mobile phase as polar, we're in normal phase mode. This setup is ideal for separating analytes based on their polarity differences, with polar mobile phases like water, methanol, or acetonitrile used to elute more polar compounds. Finally, understanding these modes and properties helps us tailor our chromatography methods to achieve optimal separation based on the chemical nature of our analytes. Let's take a closer look at the different types of columns used in reversed phase chromatography. Starting with the hydrocarbon chains, you'll notice the series of CH2 groups. These chains vary in length and functionalization, which impacts their interaction with analytes. For example, the C18, or octadecyl, columns are among the most common, featuring a long hydrocarbon chain attached to a silica support via an OC bond. This makes them highly nonpolar and ideal for separating a wide range of compounds. Next, we see the C8, or octyl, columns, which are similar but have a shorter chain, providing slightly different separation characteristics. Moving on, the C4, or butyl, columns have an even shorter chain, offering more polar interactions, which can be useful for certain analytes. Beyond the hydrocarbon chains, there are specialized phases like phenyl, TMS, cyano, and various C18 types, each introducing different chemical functionalities. These modifications enhance selectivity and can target specific interactions, making them versatile tools in chromatography. It's important to understand that these columns are designed to exploit the polarity differences between the stationary phase and the analytes, enabling effective separation. The choice of column depends on the specific properties of the compounds you're analyzing and the separation goals. So, in summary, the variety of phases, from C8 to C18 and beyond, provides a suite of options to tailor your chromatography method, optimizing for resolution, speed, and specificity. So, in this slide, we're looking at what happens when a nonpolar compound interacts with a nonpolar stationary phase. Essentially, the nonpolar compound is pushed toward a nonpolar location on the phase. This is because nonpolar substances tend to prefer nonpolar environments, which minimizes their energy by avoiding polar regions. Now, behind the scenes, we have this network of hydrogen bonds between water molecules. These bonds create a structured, interconnected network that holds the water molecules together. But when a nonpolar compound is introduced, it disrupts this network. Think of it like this. The nonpolar compound can't form hydrogen bonds with water. So, instead of fitting into the hydrogen-bonded network, it gets pushed out to a region where there are fewer or no hydrogen bonds. That is, a nonpolar zone. This process is driven by hydrophobic interactions, meaning nonpolar molecules tend to cluster together to minimize their contact with water. This helps explain why nonpolar compounds are pushed to the nonpolar areas of the stationary phase, effectively separating them based on their hydrophobicity. Understanding these interactions is key to grasping how separation techniques like chromatography work, especially when dealing with different types of compounds and their affinities for polar or nonpolar environments. Let's take a closer look at this slide. Here, we're focusing on the concept of retention and polarity, which are crucial in understanding how compounds interact with the chromatography column. On the left, we see OH and weak. These refer to functional groups that contribute to a molecule's polarity. A hydroxyl group, or OH, makes a molecule more polar, but if it's weakly interacting, it might not hold onto the stationary phase as strongly. Moving to strong. This indicates situations where the functional groups or the overall molecule's polarity result in a stronger interaction with the stationary phase, leading to longer retention times. Now, on the right, we have CH3, which is a methyl group, known for being nonpolar. This affects the overall polarity and interaction strength with the stationary phase. Then there's C18ODS, which stands for octadecylsilane, a common stationary phase in reversed phase chromatography. It's nonpolar, so it interacts more strongly with nonpolar compounds, influencing retention times based on polarity differences. Finally, note the 22 here. It's just the slide number, but it helps us keep track of where we are in the presentation. Overall, understanding how different functional groups like O and CH3 influence polarity helps us predict how compounds will behave in the chromatography process, especially when using a C18 stationary phase. This connection between polarity and retention is fundamental in optimizing separation techniques. Let's take a closer look at the differences between water and organic solvents, as illustrated here. On this slide, you can see the molecular structures of methanol, or CH3OH. You'll notice that methanol has a small, polar molecule structure. When we consider how it interacts with different stationary phases, it forms a loose network with a nonpolar stationary phase. This means that methanol doesn't strongly interact with nonpolar phases, so it moves more freely during chromatography. In contrast, water, which is also shown here, tends to form a tightly packed network through hydrogen bonding. This is a key difference. Water has a high affinity for itself due to these hydrogen bonds, creating a dense, structured network. This makes water a very polar solvent, strongly interacting with other polar compounds. Understanding these structural differences helps us grasp why water and organic solvents behave so differently in chromatography. Water's tightly packed network means it can strongly retain polar compounds, while organic solvents like methanol with their looser structure, are better at dissolving nonpolar compounds. This is fundamental to choosing the right solvent for separating specific compounds in our analyses. Let's take a look at the different mobile phase compositions and how they influence retention. Here, we see some common ratios like 70-30 and 80-20, which represent the volume ratios of methanol to water. These variations can significantly impact how compounds are separated during chromatography. For example, increasing the proportion of methanol generally decreases the polarity of the mobile phase, which can lead to faster elution of more polar compounds. Conversely, a higher water content makes the mobile phase more polar, often resulting in longer retention times for polar analytes. Now, the 60-40 ratio is also important. It's a bit more balanced and can be useful for fine-tuning separation when you're trying to optimize resolution and retention times. Overall, understanding how these different compositions affect retention helps us control and improve our separation process. Adjusting the mobile phase composition is a key tool in achieving the best separation efficiency for our specific target compounds. Now, as we look at this slide, we're examining the effect of stationary phase on our sample separation. On the left side, you can see the labels weak, medium, C4, and then moving towards stronger, C8 and C18, with C18 being an ODS or octadecylsilane phase. The key point here is that the stationary phase's chemistry greatly influences how well our samples are retained and separated. When we have a weak stationary phase, the interaction with the sample molecules is minimal, resulting in shorter retention times. As we move to medium and then to C4, C8, and finally C18 phases, the interactions become stronger, meaning the sample molecules are retained longer, which improves separation but also requires adjusting the conditions accordingly. This progression from weak to strong phases demonstrates how we can tailor the stationary phase to optimize our separation process. By selecting the appropriate phase, we can control the retention and resolution of our analytes, ultimately enhancing the effectiveness of our chromatography method. So this slide underscores the importance of understanding how different stationary phases influence separation, which is vital for achieving precise and reliable analytical results. Now, let's take a closer look at the analytical conditions used for this set of experiments. We're using a Shimpak CLCODS column, which is a common choice for separating organic compounds thanks to its good selectivity and stability. The mobile phase is a mixture of methanol and water in a 7-3 ratio. This particular solvent system helps us achieve effective separation of the benzoate esters based on their polarity. The flow rate is set at 1 milliliter per minute, which is a standard flow rate to balance between resolution and analysis time. The column temperature is maintained at 40 degrees Celsius to ensure consistent retention times and peak shapes. For injection, we're using 10 microliters, which is typical for these kinds of analyses to optimize sensitivity without overloading the column. Detection is done using UV at 254 nanometers, a wavelength suitable for aromatic compounds like benzoates because they strongly absorb in this region. Now, moving on to the peaks observed, the first one corresponds to methyl benzoate, followed by ethyl benzoate, then N-propyl benzoate, and finally N-butyl benzoate. This sequence shows how increasing the alkyl chain length affects the retention time, with longer chains generally resulting in longer retention due to increased hydrophobic interactions. Lastly, this slide highlights the effect of the stationary phase, which is crucial because changing the stationary phase can significantly influence separation efficiency and selectivity. Understanding these parameters helps us optimize our method for better resolution and more accurate analysis, fitting into the overall goal of improving our chromatographic techniques. Let's take a closer look at the key components of the gradient elution system, starting with the degasser, which is essential for removing dissolved gases from the solvents. This step helps prevent bubble formation that could disrupt the flow or affect detection. Next, we have the mixer, where different solvent streams are combined to create a gradient. This gradient is crucial for separating compounds based on their varying affinities under different solvent conditions. Moving on to concentration, which involves monitoring the concentration of analytes over time. This is often visualized as a plot, with concentration on the y-axis and time on the x-axis, showing how compounds elute from the column at different times. The pump then delivers the solvent mixture through the system, maintaining a precise flow rate. The detector is positioned downstream to identify and quantify the compounds as they elute. The oven keeps the column at a consistent temperature, which is vital for reproducibility and optimal separation. The column itself is where the actual separation happens. Different compounds travel through at different speeds depending on their interactions with the stationary phase. The injector introduces the sample into the system, ensuring it enters smoothly and evenly. The gradient elution system, as a whole, allows us to gradually change the solvent composition during the run, which enhances separation efficiency and reduces analysis time. All these components work together seamlessly to produce reliable, high-quality analytical results, helping us understand complex mixtures more effectively. Now, let's take a look at the methanol ratio in the mobile phase. As you can see, choosing the right MP ratio is crucial for good separation and a short analysis time. For example, when we use a water to methanol ratio of 2 to 8, we get optimal separation efficiency. Similarly, a water to methanol ratio of 6 to 4 will change the separation dynamics, so adjusting this ratio allows us to fine-tune the process. This slide also highlights that we're using a C18 type column, which is common in many chromatography applications due to its versatility. Another important point here is the idea of gradually changing the mobile phase composition during the analysis. This is where gradient elution comes in. By gradually increasing or decreasing the solvent strength, we can improve separation of complex mixtures more efficiently. In contrast, isocratic elution maintains a constant mobile phase throughout the run, which is simpler but might not always give the best results for complex samples. So, understanding when to use isocratic versus gradient elution and how to optimize the MP ratio is key to achieving faster, more effective separations in our chromatography workflows. Let's take a closer look at the pump, which plays a crucial role in our chromatography system. It's responsible for delivering the mobile phase consistently and at the correct pressure, ensuring smooth and reproducible flow through the system. Speaking of the mobile phase, this is the solvent or mixture of solvents that carries our sample through the column. Its composition and flow rate are vital because they directly influence our separation efficiency and analysis results. Now, to manage the complex requirements of different analyses, we often use a quaternary gradient system. This system allows us to mix 4 different solvents in precise ratios, and we can change these ratios during the run. This flexibility is especially important when dealing with complex samples or when we need to optimize our separation. Putting it all together, these components, the pump, mobile phase, and gradient system, are interconnected. The pump delivers the mobile phase under controlled conditions, and the gradient system enables us to modify the solvent composition dynamically. Understanding how these elements work together helps us achieve accurate, high-resolution separations, which is at the heart of our overall analytical goals. Now, let's take a closer look at the key points on this slide. First, it's important to understand that effective communication is the foundation of successful teamwork and project management. When we communicate clearly, we reduce misunderstandings and ensure everyone is on the same page. Next, I want to highlight the role of active listening. This isn't just about hearing words, it's about truly engaging with what others are saying, asking clarifying questions, and showing that you value their input. This builds trust and fosters a collaborative environment. Another crucial aspect is adapting our communication style to different audiences. Whether we're speaking to technical teams, executive leadership, or clients, tailoring our message helps ensure it resonates and is understood. Finally, connecting these points to the overall theme, It's clear that mastering these communication skills not only improves individual relationships, but also drives overall project success. Strong communication underpins all the strategies we've discussed so far, reinforcing the importance of this skill set in achieving our goals. Let's take a look at some of the commonly used acids in buffer solutions for HPLC mobile phases. First, we have phosphoric acid, which has multiple pK values at 2.1, 7.2, and 12.3. These multiple pK values reflect its ability to act as a buffer over a wide pH range. Next is acetic acid, with a pK of 4.8. It's a weaker acid compared to phosphoric acid, but still quite effective for certain pH adjustments. Then we have citric acid, which is triprotic, with pK values at 3.1, 4.8, and 6.4. Its multiple dissociation steps make it versatile for buffering over various pH levels. Now, regarding concentration, if your goal is merely to adjust pH, around 10 millimoles per liter is usually sufficient. It's a practical concentration that provides effective buffering without unnecessary excess. Moving to the requirements for these buffer solutions, there are a few key points. First, they should have high buffering power at the pH you need. This ensures stable conditions during your analysis. Second, they shouldn't adversely affect detection methods, so they must be compatible with your detection system. Third, they must not damage the chromatography column or other equipment, which is crucial for maintaining system longevity. And finally, they should be inexpensive, making routine analyses more feasible in a typical laboratory setting. In summary, selecting the right buffer involves balancing effective pH control, compatibility, equipment safety, and cost. These factors are essential for reliable and reproducible HPLC results. Let's take a closer look at the differences between integrated and modular HPLC systems. On one hand, with integrated systems, we focus on simplicity and automation, making the operation straightforward and support easier. These are ideal for routine analysis, where efficiency and ease of use are key. They tend to be dependent on your budget, as integrated systems can be more cost-effective for standard applications. On the other hand, modular systems offer greater flexibility and expandability. They allow you to customize and adapt the setup based on your specific needs, which is particularly useful in R&D or multi-purpose environments. However, they're more dependent on the application, requiring careful planning as your needs evolve. Overall, choosing between integrated and modular HPLC depends on your specific requirements, whether you prioritize simplicity and automation for routine tasks, or flexibility and expandability for more complex or research-focused work. Both approaches have their strengths, and understanding these key points helps us make the best choice for our laboratory. Let's explore how we can produce the next generation UHPLC without compromising on performance. The development concept centers around creating a system that is both versatile and powerful. For instance, it can handle pretreatment and multi-dimensional liquid chromatography with precise valve control to ensure seamless operation. When it comes to accuracy and precision, especially in ultra-fast analysis, this system aims to deliver the highest standards. We're also focusing on speeding up the injection process while minimizing carryover, which is crucial for maintaining data integrity. Additionally, the system boasts the highest pressure range combined with the widest flow rate range, allowing for greater flexibility and capability. To maximize efficiency, it features the fastest cycle times, which helps increase sample throughput significantly. We're also committed to reducing solvent consumption, aligning with environmental sustainability goals. Overall, this approach is about maximizing performance, expandability, and throughput, covering all bases from resolution and speed to system scalability. Whether it's HPLC, UFLC, or UHPLC, our goal is to push the boundaries of what's possible, delivering a system that's not only high-performing, but also adaptable to future needs. So in this slide, we're focusing on what chromatography actually is, specifically highlighting the outline of HPLC analysis. First, let's talk about the separation mechanism. This is the core of chromatography. It involves how different components in a mixture are separated based on their interactions with the stationary and mobile phases. Essentially, each compound moves at a different rate because of its unique affinity for these phases. Next, we look at the hardware mechanism, which refers to the equipment used in HPLC. This includes pumps, columns, detectors, and the entire system that facilitates the separation process. Understanding how this hardware works helps us optimize the analysis and ensure accurate results. Finally, the contents of this slide give us a broad overview, connecting the theoretical separation principles with the practical aspects of the instrumentation. Overall, this slide ties into our larger theme of understanding how HPLC allows us to analyze complex mixtures efficiently and precisely. Let's take a closer look at the pump type and how it influences our system. The choice of pump is crucial because it affects the flow rate, pressure, and overall stability of the detector operation. Different pump types, such as diaphragm or piston pumps, have unique advantages depending on the application's requirements. Next, we have the injector connection, which is another vital component. A secure and reliable connection ensures consistent injection of samples or reagents without leaks or interruptions. Properly designed injector connections help maintain system integrity and improve reproducibility. Moving on, let's consider the cell structures used in typical detectors. The hardware mechanism involves the physical design of the detection cell, which is fundamental to achieving accurate measurements. The cell must be precisely engineered to optimize factors like optical path length, flow dynamics, and minimizing noise. All these components, pump type, injector connection, and cell structure, are interconnected. They form the core hardware mechanisms that enable our detectors to perform reliably and accurately. Understanding these elements helps us troubleshoot, improve, and innovate in our detection systems, ensuring high-quality results across various applications. All right, let's take a closer look at the plunger reciprocating pump and its key components. First, we have the diaphragm, which acts as a flexible barrier, helping to create the necessary pressure differences. Next is the seal wash, which is crucial for maintaining a proper seal and preventing leaks during operation. The mixture ratio of 90:10 water to IPA is important for cleaning and ensuring the pump functions smoothly. Moving on, the pump handles volumes of 10 to 100 microliters, making it suitable for precise applications. The pump head is where the action happens. It's the part that moves the fluid through the system. The check valve ensures unidirectional flow, so the fluid doesn't backtrack, maintaining efficient operation. The plunger seal is vital for preventing leaks around the plunger itself, which moves back and forth to draw in and push out fluid. The plunger, of course, is the core component that moves reciprocally, powered by the motor and cam mechanism. The motor and cam work together to convert rotational motion into linear motion, driving the plunger back and forth smoothly. Putting it all together, this reciprocating pump is designed for precision and reliability, especially in tasks requiring small volume handling. Every component plays a role in ensuring consistent flow and minimal contamination, which ties back to our overall theme of accurate fluid control in complex systems. Let's take a closer look at the components involved in this part of the system, the plunger and the plunger seal. The plunger is essentially the moving part that pushes or pulls fluid within the mechanism. It plays a crucial role in controlling the flow and pressure. The plunger seal, on the other hand, is what prevents fluid from leaking past the plunger as it moves. It's a vital component for maintaining system integrity and efficiency. Together, these parts ensure smooth operation and help us achieve precise control. Understanding how they work and their importance really ties into the overall theme of maintaining reliable and effective system performance. Let's take a closer look at the key components involved in precise fluid delivery. The pump head is designed to handle volumes ranging from 10 to 100 microliters, making it versatile for different applications. The check valve plays a critical role in preventing backflow. ensuring that the fluid moves in the correct direction. The plunger seal is essential for maintaining a tight seal around the plunger, which helps achieve accurate dispensing. Speaking of the plunger, it's the part that moves to draw in or push out the fluid. The motor and cam work together to drive the plunger's movement smoothly and precisely. Altogether, these components form a reliable system that ensures accurate and controlled fluid transfer, which is fundamental to the overall performance of the pump. Now, let's take a closer look at the solvent delivery pump, specifically the plunger pump schematic diagram. As you can see, the motor or cam is responsible for driving the plunger back and forth. This movement is what allows precise control of the solvent flow, typically ranging from 10 to 100 microliters. The pump head houses the key components, including the check valve, which ensures that the solvent flows in only one direction, preventing backflow. The plunger seal is critical for maintaining a tight seal around the plunger, preventing leaks and ensuring consistent delivery. When the plunger moves forward, it draws solvent into the pump, and when it moves back, it pushes the solvent out through the outlet. This mechanism is fundamental for accurate and reliable solvent delivery in many analytical applications, tying into our overall theme of precise fluid control in laboratory systems. Now, let's take a closer look at the schematic diagram of the solvent delivery plunger pump. As you can see, the core component is the plunger, which moves back and forth to deliver precise volumes of solvent, anywhere from 10 to 100 microliters, depending on the application. The movement of the plunger is driven by a motor and cam mechanism, which ensures smooth and controlled operation. The pump head houses the plunger and connects to check valves that prevent backflow, maintaining a consistent flow direction. The plunger seal is crucial here, as it maintains the integrity of the seal around the plunger, preventing leaks and ensuring accurate volume delivery. Overall, this setup allows for highly precise and reliable solvent delivery, which is essential in many analytical and preparative processes. This schematic ties into our broader discussion on how fluid control systems play a vital role in achieving reproducible and high-quality results. Now, let's take a closer look at the solvent delivery pump, specifically the plunger pump schematic diagram. As you can see, the core component is the plunger, which is driven by a motor and cam system. This setup allows precise control of the movement, typically delivering between 10 to 100 microliters per cycle. The plunger is sealed with a plunger seal to prevent leaks and ensure accurate fluid movement. The pump head holds the plunger and connects to check valves that control the flow direction. These check valves are crucial. They prevent backflow and maintain a steady, unidirectional flow of solvent. Overall, this schematic highlights how the plunger pump functions as a highly precise and reliable component in solvent delivery, which is essential for consistent chromatography results.